Hey, so I wanted to make a quick video about the synthesis of ethers or synthesizing ethers. There are a few ways to do this. An ether is an oxygen connected to two different carbon groups. And in this case, we're going to first start with ethanol heated up in the presence of an acid. So we will draw our ethanol. And we can do this just to signify an acid, or we can draw one in. I think sulfuric acid is commonly used. We can use hydronium as well. For this case, I guess we can let's draw in hydronium, because that looks like familiar enough, right? Okay, and the first thing that's going to take place is a proton transfer. And we're kind of setting up our alcohol here, our ethanol, for setting up a good leaving group is what we're doing, right? Because this isn't going to leave on its own. Hydroxide is a terrible leaving group. And so what happens is first we have a proton transfer. So the electron pair on the oxygen here is going to reach into the acid and take a proton. And then what we're going to have is something that should look familiar. And this is now H2O at the end. And then what we're going to do next is we have our ethanol solution still. And we are going to use this oxygen, and what's going to take place is an SN2 reaction, or a nucleophilic attack if we're just looking at the mechanism. And so we have our electron pair here, and it's going to detect this partially. Remember, we have a partially positive carbon here because of this oxygen it's connected to. And so what this is going to do is going to reach over and attack this carbon. And then H2O, being the good leaving group it is now, will leave. And then finally, what we're going to have is, I'm going to draw like this, is this guy here, right? But we're going to end it with a proton transfer, because we want to get rid of this hydrogen right here to get our ether there. So we've kind of like come full circle, right? We've kind of sandwiched this thing in. And you can use another ethanol for this. You can also use the water that's also present now. All you're going to do is whichever oxygen you want to use, both of these can go. Let's just use the ethanol we have in abundance here. And it's going to go ahead and grab that hydrogen, and we're going to end with our final product, which is a symmetrical ether. And this is the industrial method of doing it. It isn't ideal. It's great for what they need it. But when we're synthesizing ether, if this is the only ether we can get from this synthesis, it's not really that helpful, right? So I wanted to go over another way of synthesizing ethers, and that is, let me move this buddy down here for later, and that is right here for us, the Williamson ether synthesis. Where's my okay? And this way of synthesizing ether is going to be a little bit more helpful. Gives us the freedom to create whatever kind of ether we want to create, right? So for the Williamson ether synthesis, we can what we're going to need is an alcohol and an alkyl halide, preferably a methyl or a primary halide, because we will be doing an SN2 reaction, and SN2 reactions will work best and follow through on methyl or primary alkyl halides, right? And so let's get started. So with this one, let's say we have our alcohol of choice. And then what we're going to do is we're going to first start with deprotonating. So remember with the other one, we were protonating and then removing as a leaving group, and then SN2 and then deprotonating. This one, it's going to be 2 steps, and we're going to start with sodium hydride as our strong base. The hydrogen here is going to be the one doing the deprotonating. And then what we're going to have is our oxygen connected to the R group. And now that this oxygen is negatively charged, it will act as our nucleophile. And here we can have our alkyl halide, so we can use, let's try methyl iodine. And then this oxygen will act on this portion of the methyl iodide, and that is because this portion is the positive portion here, right? Just keep in mind. And then what you're going to end up having is that. And you can do this with more elaborate alcohols as long as it obeys this like SN2 reaction here. And then you have that strong base to deprotonate. You're pretty much set. So let's show us an example, right? Okay, so let's say for example, we want to get this as our product, right? And this is an ether. We see here that it has an ethyl group here, and then here it has a phenyl group here. And so remember, we're going to want to start with an alcohol and an alkyl halide. So now it's our job to figure out which side we're going to keep the alcohol on, if we're going to keep it attached to the phenyl group, or if we're going to make it attached to the ethyl group. And we can kind of just play out both scenarios and see what works best. And we're going to find out soon that, remember, we're going to keep in mind that this is going to end in an SN2 reaction. So we want to make sure whatever we set up as our alkyl halide can be attacked with through SN2, right? So let's say, for example, we choose to keep the halide on the phenyl, right? And we have like iodide attached to it. And then we have the alcohol part of it attached to the ethyl group, right? The first thing we're going to do here is we're going to deprotonate with our strong base, like so. And that's when we have our nucleophile set up for an SN2 reaction. But then look at what's going to happen here. Remember, we can't do SN2 on sp2 hybridized. This is sp2 hybridized, or we also recognized it from like our last course as tertiary. So this can't act as a nucleophile and attack this carbon right here and cause this to be a leaving group, because this isn't a spot that can be. It will not take place as a SN2, right? So this cannot happen. However, if we were now to keep the alcohol on the phenyl ring, right, and make the alkyl halide attached to the ethyl group, this is what it would look like, right? We're gonna now have our alcohol instead attached here. And then we're going to start, remember, deprotonation. We have our strong base. The hydrogen is going to deprotonate this alcohol, and that's going to give us this phenyl ring with our now ready to attack
nucleophile.
And that's when we use now the way it's like looks there, and that's when we use our alkyl halide that's attached to an ethyl group, right? And so this nucleophile is going to attack here, which is going to cause this iodide to be a good leaving group, and that's going to result in the product we were aiming to get, right? This looks a lot like this guy here. And we did that by choosing, remember, setting it up with an alcohol and alkyl halide. We have our strong base, and then we just we do the deprotonation, and then we do the SN2 reaction here. Right. And then the last method of synthesizing ethers in chapter 13 is through alkoxymercuration demercuration, which is very similar to the addition reaction to alkenes that we did, which added OH Markovnikov to the double bond. And so OH would be on the more substituted side, and then hydrogen would be placed on the less substituted side. And this is what we would get from the reaction. We know there's like one here. If we had just done the addition reaction with water, with H2O. However, with alkoxymercuration demercuration, instead of using H2O, you use an alcohol. So let's go down to here. And what would that look like? Well, it would be the same thing, Markovnikov addition of the OR group on the more substituted side and hydrogen on the less substituted side. And so what we would get would be there's an H there, would be this. And this would be our ether. It's not really talked about as much, but I thought it'd be helpful just to show and use if you need. But I think we would mainly be focusing on Williamson ether synthesis, at least for this course.